Welcome back to The Explainer. So, if you've spent literally any time marveling at the incredibly realistic images and videos AI is churning out these days, you've actually been staring right at the output of a completely hidden piece of architecture. Today, we are demystifying the invisible engine that makes the whole shebang possible, the Variational Autoencoder, or VAE. Just think about the absolute titans of modern generative AI right now. Stable Diffusion, Sora, Flux. Sure, they might seem totally different on the surface, but here's the crazy part. Every single modern latent diffusion and flow matching model relies on the exact same hidden input mechanism. They all share one invisible first layer to actually make their magic work.
Which brings us to the obvious question. What exactly is a VAE? Why is this specific acronym the undisputed engine of generative AI? And how in the world did a clever math trick turn a basic compression tool into an absolute world-building machine?
Okay, let's dive into this. We'll kick things off with the autoencoder problem, uncover the VAE magic trick, walk through exactly how to build your own, navigate some common pitfalls and solutions, and wrap up with the modern AI stack.
Part 1. The autoencoder problem and the fatal flaws of memorization.
To really grasp why a VAE is such a game changer, we first have to look at why a plain old traditional autoencoder totally fails at generating new content. Imagine a standard autoencoder crushing a 784-pixel image of a handwritten digit down to just 16 numbers, and then rebuilding it. It does this perfectly, right? But it does it by simply memorizing the input data. And that is its fatal flaw. Its compressed code space is just a totally unstructured, lumpy mess. It's basically a compression model dressed up as an AI. If you pick a random coordinate in that space and decode it, you're just going to get static noise. Now, a VAE, on the other hand, forces that code space into a beautifully clean, smooth, isotropic Gaussian distribution. You can actually pluck a random sample from this structured space, decode it, and bam, you get a completely new mathematically plausible digit.
All right, moving to part 2, the VAE magic trick, also known as the reparameterization trick.
Now, what's really interesting about this is how exactly we force a neural network to make that code space so perfectly smooth. The secret sauce is a massive 2013 breakthrough by Diederik Kingma. See, a VAE encoder doesn't just output a single point, it outputs a probability distribution. But there's a catch. Sampling a random point from a distribution isn't differentiable. That means your neural network suddenly can't learn using standard backpropagation. It just hits a brick wall. So the magic trick is to rewrite the sample, which we'll call z, as a deterministic function, using the mean and standard deviation, and then you add in pure external noise. By doing that, you completely bypass the randomness. Gradients can flow smoothly backward through the mean and standard deviation, and boom, the network can actually learn.
To actually train this thing, we use a loss function called the ELBO. It essentially balances two competing goals: accurately reconstructing the image, and a penalty called the KL penalty, which forces the distribution to look like a clean Gaussian turf. Back in 2017, researcher Irina Higgins introduced the beta VA, which basically slopped a volume knob right onto that KL penalty. If you turn that beta knob down below 1, you get much sharper image samples, but your code space gets untidy. On the flip side, if you crank beta up past 1, your code space becomes beautifully clean and disentangled, but your final images are going to end up blurrier. It is an incredibly delicate, constant tug of war.
Part 3. Building your own VAE. 4 pragmatic steps to generation. It is actually surprisingly straightforward to build a tiny pedagogical VAE yourself in Python. Here is the 4-step playbook. Step 1. The encoder forward pass. And hey, massive pro tip here, make sure you use the log of sigma squared. If you don't do this, your network output gets constrained, and your gradients will likely just die right out at 0. Step 2. Apply that reparameterization trick we just talked about and decode. Step 3 is calculating your ELBO loss. Now absolutely use the exact closed form KL penalty here. Because both distributions are Gaussian, the math is exact. Believe it or not, I still see developers in 2026 inexplicably shipping code using Monte Carlo estimates for this, which literally makes the whole thing 3 times slower for zero reason. Seriously, please stop doing that. Finally, step 4, you generate. Push pure noise through the decoder and watch a brand new image appear.
Part 4. Pitfalls and solutions, because you're definitely going to encounter some traps.
Let's be real. It's not always sunshine and perfect gradients. You are inevitably going to face some hurdles, so here are the biggest VAE failures and their exact production fixes. First up is posterior collapse. This nightmare happens when your KL penalty is just way too aggressive. It basically bullies the latent space into holding zero information, meaning the encoder just completely ignores the input. The fix? Beta annealing. You start your beta at 0 and slowly, gently ramp it up to 1. The next pitfall is blurry samples. A Gaussian decoder optimizes for mean squared error, which naturally just averages out the details and leaves you with a fuzzy, soft image. The modern production fix is to either use a discrete decoder like a VAE or do what Stable Diffusion does. Use the VAE purely to compress and then stack a heavy-hitting diffusion model directly on top of those latents. Lastly, don't starve your model with a latent dimension that's way too small. A 16D space is fine for a tiny MNIST digit, but if you are dealing with megapixel images, you really need to scale up to 2048 dimensions.
Which brings us to part 5, the modern AI stack and where VAEs live in the wild today.
And this brilliantly illustrates exactly how VAEs are deployed in the real world right now. They are foundational across almost every medium you can think of. But VAEs rarely ship entirely standalone anymore. They are the ultimate supporting character. If you're working with images, you grab the Stable Diffusion or Flux VAE. For audio generation, you're pulling Meta's encode or Descript's DAC. For video, you rely on Saurus Patches or the WAN VAE. And if you are doing transformer modeling, you need discrete latents, so you lean heavily on a VQ VAE. The pattern is completely universal across the board. The VAE does the coarse, heavy compression on the outside, and a diffusion model or transformer does the actual heavy lifting on the inside.
To put that heavy lifting into perspective, just think about the number 32. That is the massive spatial downsample factor achieved by Stable Diffusion's VAE alone. It takes a massive 512 by 512 image and crushes it into a tiny 64 by 64 grid. By shrinking the playground by a factor of 32, the diffusion model can operate insanely fast before finally handing it back to the VAE to decompress.
But fair warning, that final decompression step is exactly where servers go to die. Here are your crucial survival tips, especially for consumer GPUs. The VAE is the absolute hottest path in a diffusion server. Upsampling a tiny 128 by 128 latent grid back to a massive megapixel image creates this gigantic activation memory peak that will absolutely crash your GPU. To survive this, you literally must slice or tile the decode. Tiling trades a tiny, barely visible seam artifact to keep your memory usage completely manageable. Also, always use a BF16 decoder or an FP16 fixed variant. If you try to use standard FP32 numerics for that final massive resize, you will get silent, not a number errors that will completely ruin your high-res outputs. Just don't do it.
So the absolute crucial takeaway here is that understanding the VAE means understanding the bedrock of modern AI generation. Once you grasp this invisible engine, the whole generative AI landscape just clicks into place. Which leaves me with a final provocative question for you. Are you ready to take what you've learned today, leave continuous data behind, and extend this into your very own mini VQ VAE by replacing that continuous variable with a nearest neighbor codebook? The blueprint is in your hands now. Go build something amazing.